Let's look at compound interest compounded more often than annually. Suppose you get a graduation gift of $1,000. You deposit it into an account which grows at 5% annual interest compounded monthly. How much do you have in 40 years? Well, first, what do we mean by interest compounded monthly? We mean that you do not have to wait a year to start obtaining interest. Each month, whatever interest you have earned that month is added to your account. The advantage of this, you earn interest on your interest from previous months. Here's the formula we'd use. If we deposit P into an account which grows at an annual interest rate of R is expressed as a decimal, then after T years we will have F equals P times 1 plus R over M to the N, where M is the number of times compounded per year, and N is the total number of compounding periods, which is T times N. So in other words, P is the amount of money we start with. You can think of that as meaning present. F is the future amount of money after the money sits in the account. R is the interest rate, M is the number of times compounded per year, and N is the number of compounding periods, which is T times M, the number of years times the number of compounding periods per year. That's N. Now the formula from last time for interest compounded annually was F equals P times 1 plus R to the T. Notice the similarities. Actually, if you plug in, so these formulas are similar. Now in this particular case, F equals what? We don't know. We don't know what F is. That's what we want to find out. We don't know what our money will grow to in the future. So F is just one big question mark. P is 1,000. R is 0.05. Notice that R is not 5. The interest rate expressed as a decimal is 0.05. Because when you take a percent and express it as a decimal, you move the decimal point over a couple of places. So R equals 0.05. T is 40. That's the number of years. M equals 12. If you have interest compounded monthly, then your interest is compounded 12 times per year. M is the number of times compounded per year. And in this case, N is TM. T is the number of years, M is the number of times compounded per year, and we just put it in like that. So 1,000 times 1 plus 0.05 over 12 raised to the 40 times 12. Here's the way I'd put that in my calculator. 1,000 times 1 plus 0.05 over 12 raised to the 40 times 12 in parentheses. That's $7,358.41. Now, we wanted to calculate this amount, so that's what we entered. 1,000 times 1 plus 0.05 over 12, that little caret sign, and in parentheses 40 times 12, 7358.41. What if we had entered this instead? Notice, looks the same, except the 40 times 12 is not in parentheses. This gives us a wrong answer. Why? Now, it's the order of operations. Let's review the order of operations. What is 2 plus 3 times 4? Is it 2 plus 3 times 4? In other words, 5 times 4, or 20? Or is it 2 plus 3 times 4? In other words, 2 plus 12, or 14. The order of operations that's used by a calculator, used by mathematicians, is parentheses, exponents, multiplication and division, addition and subtraction. PEMDAS. PEMDAS is this nonsense word which we sometimes use to remember the order of operations. Parentheses, exponents, multiplication and division, addition and subtraction. Please excuse my dear Aunt Sally is another way of remembering that. A mnemonic for remembering PEMDAS, or parentheses, exponents, multiplication and division, addition and subtraction. Please excuse my dear Aunt Sally. So again, the order of operations looks like this. 2 plus 3 times 4. Notice that the 3 times 4, the multiplication gets done first before the addition gets done. So 2 plus 3 times 4 is interpreted as first the 3 times 4 and then the 2. So 3 times 4 is 12. That gets done first, and then the 2 gets added to it, and we end up with 14. So 2 plus 3 times 4 is 14. That's why 1,000 times 1 plus 0.05 over 12 raised to the 40 times 12 gives us the wrong answer, because the calculator is interpreting that as 1,000 times 1 plus 0.05 over 12 raised to the 40th, all times 12, and that's not what we want. We don't want that whole thing times 12. We want the 40 times 12 in parentheses. So again, it would first calculate the 1 plus 0.05 over 12, that's in parentheses. Then it would do the exponent, the 40. Then it would do the multiplication, 1,000, and then times that. And that's not what we want. That gives us $14,171.42. And I wish we had that amount, but that's not the correct amount. Instead, what we want to enter is this. And we get $7,358.41. So again, notice the 40 times 12 is in parentheses. Suppose you get a graduation gift of $1,000. You deposit it into an account which grows at 5% annual interest. How much do you have in 40 years if the interest is compounded annually? We saw in the previous video, that's $7,039.99. If it's compounded monthly, it's $7,358.41. What if it's compounded daily? So I would like you to take a moment, just pause the video, and use that formula, the formula that we used for monthly compounded interest. See if you can figure out how much money we'd get if we compounded interest daily. Go ahead and pause the video for a moment. If we pause the video, well, if we calculate it using daily compounded interest, notice that everything's the same, $1,000, 0.05, except now M, the number of times it's compounded per year, is 365. It's no longer 12. It's not monthly compounded interest. It's daily compounded interest. So that's now 365. And we end up with 1,000 times 1 plus 0.05 over 365. And that's raised to the, in parentheses, 40 times 365, which is 7388.04. So notice we do get a little extra money. In going from annual to monthly compounded interest, we got roughly an additional $300. But in going from monthly to daily compounded interest, now we only earned about another $30. So not a lot more money. So 7388.04 is what we end up with if we have interest compounded daily. Now, suppose you get a graduation gift of $1,000. How much do you have in 40 years if the money grows at 1% annual interest compounded daily? If it's 5%, you get $7388.04. How about if you get 1%? I want you to take a moment and guess what you'd end up with. Go ahead and pause the video a moment. How much would you get if you invest $1,000 at 1% annual interest compounded daily? Here's the amount we got. Everything's the same, 1,000 times 1 plus 0.01, so instead of 0.05, it's 0.01 over 365, raised to the 40 times 365. So again, that's what you'd enter into your calculator, and what you'd end up with is $1,491.82. Look at that huge difference. If you invest at 5%, you have $73.88. If you invest at 1%, you have $14.91. That is a huge difference. There's a lesson in this. Although you don't want to invest too wildly, if you invest too conservatively and your rate of return is really low, then you may not have much money in the end to show for your investment. So it pays to not invest too conservatively, because even though your money may be, quote, safe, it's really not going to grow at a decent rate of return. Let's say we deposit a certain amount of money today into an account which grows at 3.45 annual interest compounded quarterly. Determine how much we need to deposit now if we want to have $14,000 5 years from now. So here's the formula we'd use. Again, same formula, F equals P times 1 plus R over M to the N. Why don't you go ahead and take a moment and see if you can figure out the answer to this problem. Let me give you a hint. In this case, F is 14,000. Whoops, that's too much of a hint. F is 14,000. P is what we don't know. So take a moment, go ahead and calculate it, pause the video. So here's what we end up with. 14,000 equals P times 1 plus 0.0345. Notice 3.45% interest is 0.0345 expressed as a decimal. Divided by 4, so M is the number of times compounded per year, that's 4, and then raised to the N. N is 5 times 4. 5 years times 4 times compounded per year. And when we calculate this, after dividing both sides by that messy expression on the right, we end up with 14,000 divided by 1 plus 0.0345 over 4 raised to 5 times 4, and that gives us $11,790.53.